All right, for Unit 4, we're going to start exponential functions. And an exponential function is just a function where our inputs are in our exponent. Our parent exponential function, it looks like this. F of x equals a times b to the power of x minus h plus k. And hopefully you've seen some of those values before. We've used a, h, and k before. That's for they describe all the transformations applied to our functions. We don't really have a parent function form because every function is different because the base of your exponent is different. That's what your b stands for. So you kind of have two different parent functions, one that represents exponential growth and one that represents exponential decay. We're just going to use 2 and 1/2, and we'll graph those in a sec. Before we do that, let's quickly define a, b, h, and k again like we have in the past. Let's do our h and our k. H is your horizontal shift. K is our vertical shift up and down. A has normally been the vertical stretch or compression. And it still will represent a stretch or compression. But in terms of growth or decay for these word problems, it's our starting amount. Okay, so in order for something to increase or something to grow or decay exponentially, you need to start with some amount. So that's what our A value is going to represent in the word problems, which we'll do at the end here, and you'll have some on the homework. B is the base of your exponent, and the base determines whether it is growth or decay. So it's your growth or decay factor, right? And then again, you're going to have some asymptotes. And you had asymptotes when we were graphing rational functions in Unit 5, right before winter break. More specifically, you're always going to have a horizontal asymptote, and it's always going to be at y equals k, the vertical shift up and down. If you remember, the definition of an asymptote is a line that a graphed function approaches as the value of x gets very large or small. Okay, we usually graph the asymptotes using a dotted line. It helps us sketch the shape of that function. So let's go ahead and graph our two parent functions here. This first function is going to represent exponential growth, and that would be because the base is greater than 1. So let's go list that up here. Sorry about that for growth and decay. I'm going to slide this down a little bit. But exponential growth would be when our base is greater than 1, and exponential decay would be when our base is less than 1 and greater than 0. If the base is negative, it's neither growth nor decay. It's still an exponential function, but it's not representing a real-life growth or decay exponential situation. And then your vertical shift, we can also put here that k is your horizontal asymptote. So we have that written in a couple places. So we know this is exponential growth. We're going to graph by using a table. Some negative values, 0, 1, and 2. Let's see what we get. Remember, anything to a negative exponent takes that base and it flips it. So this becomes 1 over 2 to the power of 1. Anything to the power of 0 is 1. 2 to the power of 1 is 2, and 2 squared is 4. So we're going to have a function that looks like this. Okay. There is no k value right? There's no vertical shift up and down. This is our parent function. We don't have any transformations applied here. So that means your horizontal asymptote is at y equals k. And as x gets infinitely smaller, as it approaches negative, it's going to get really, really close to that horizontal asymptote, and our graph looks like this. Exponential growth, it's curving up. Hopefully you can see our y-intercept is 1 because we don't have an a value, so you would just treat a as 1 times 2 to the power of x. Let's list our domain and our range. Domain is all real numbers. Range is everything above the horizontal asymptote, so above 0, but not touching. And then you're not going to be quizzed or tested on this until next unit, so it's just good practice, but let's talk about end behavior again. As x approaches infinity and as x approaches negative infinity. Well, as we go to the right, this function is going up, so f of x is approaching positive infinity. As we go to the left, this function is not approaching negative infinity. We don't cross the horizontal asymptote, so it's approaching 0. Okay. We never cross the horizontal asymptote, so it's going to get really, really close to 0, the left side of this graph. Great. Let's change that to y equals 0 because that's our k value. Let's try an exponential decay function. This would be exponential decay because the base is less than 1, greater than 0. Something else I want to put on here, when we have some word problems in a sec, you're going to see percent increases. For growth, if we want to write an exponential growth function with a percent increase, our base would just equal 1 plus whatever that percent increase is. Okay, and don't forget percents, we want to write them as decimals first. So then for decay, this would be 1 minus our percent decrease. And you'll see examples like those in just a sec. Okay, let's make another table. I'm going to use a few more negative values here because our base is a fraction, and I want that fraction to flip and give us whole numbers. So negative 2, remember the negative 2 takes the 1/2, flips your 1/2, and it becomes 2 over 1 squared, which is 4. Negative 1 just becomes your 2, 0 is your 1, and 1 is your 1/2. So let's go graph this function. 1, 1/2, 0, 1, negative 1, 2, and negative 2, 4. So we have something that looks like this. Hopefully you can see it's decay because it's going down. Again, horizontal asymptote at the x-axis because there's no k value. Y equals 0. Let's go ahead and put domain and range and end behavior. Domain is all real numbers. Range, everything greater than 0. And then our end behavior as x approaches infinity and as x approaches negative infinity. As we approach infinity, this function is now approaching the horizontal asymptote at 0. As we go to the right, it's approaching 0. As we go to the left, it's approaching positive infinity, the graph. Okay. Again, just a little review with end behavior. You're not going to have it on your homework or be quizzed or tested on it this unit. It's just good practice before we review every function in Unit 6. Okay, let's graph 2 more functions, one that's exponential growth, one that's decay. We'll do number 1 together. This is an exponential decay function because the base is less than 1, greater than 0. We're going to make a table, and we have some shifts that are applied here, okay? So let's make our table. Remember, 0.8, that's the same as 4/5 times 5 plus 1. To the power of x. First thing we want to do is let's plot this horizontal asymptote. We have a shift up 1. So we have our horizontal asymptote at y equals 1. And then we can plug some values in. At least 3 points is good for these functions. At least 3 points should be enough to see this shape using those 3 points in the asymptote. So I'm going to use a negative value, 0, and a positive value. Remember, when you plug in a negative, it flips that fraction, or it flips the base. And we get 25 over 4 plus 1, which is 29 over 4. Right? Write 1 as 4 over 4. 0 just gets us 5 plus 1, so 6. And then positive 1, that would be 5 times 4/5 plus 1, and our 5 eliminates, so we get 4 plus 1, which is 5. Now, I was adding 1 to every single one of these outputs. So I know we've talked about graphing from your new origin after you've shifted that function. But because I was adding 1 to all of these outputs, we're graphing from our original origin here. Okay? We're not graphing from the asymptote as our x-axis. We're just going to use the asymptote to help us shape the curve of that graph. So negative 1, 29 over 4 is 7 1/4. So negative 1, 1, 2, 3, 4, 5, 6, 7 1/4, 0, 6, and 1, 5. And hopefully you can see this graph curving down. That's about the best I can do here. I mean, it would continue this direction, not crossing your horizontal asymptote. It's a little bit flatter than the 1/2. That's because 0.8, that's pretty close to 0, right? So the closer you get to 0, the more flat that curve is going to be. The further you get away from 0, the steeper that graph is for decay or growth. Okay, why don't you guys try 2 on your own. Let the video pause, work it out, and then I'll put the solution up when you are done. Remember, start with the asymptote, and then make a table with some negative values and some positive values. Okay, for number 2, there was no shift up and down, so the horizontal asymptote was the x-axis. There was a shift left to right, so really you're not going to draw a new y-axis. You're just going to apply the shift to the right when you're plugging these values in for x. So let's just use negative 1, 0, 1, and then I would go 1 more, because these first 3 values, they're going to be pretty close together. Negative 1 would have gotten you 2/9. 0 would get you 2/3. 1 would get you 2. And 2 would get you 6. So we have negative 1, 2/9. 0, 2/3. 1, 2. And 2, 6. You can see this is growth because it's curving up. You can see it's really, really steep because that base is, it's not that 3 is not that close to 1. It's really, really steep. It's tripling every single input. Okay. Let's put domain and range. Why not? Domain, all real numbers. Range, everything greater than 0. For number 1, domain was all real numbers, and range was everything greater than 1. Vertical shift up 1. Okay, the last thing I would like to finish with would be these 2 word problems. We'll do 3 together and let you try 4. I picked the humpback whale example because I selfishly wanted to share a picture that I took from over break out in Hawaii, the humpback whales. This example is Australian humpback whales. I don't really know if there's a difference, but we're going to graph this representation of the whale population starting at 350 and increasing about 14% each year. All right, you're going to need a calculator, definitely, so we'll use Desmos. But your function equation should look like this. 350, starting amount. Remember, here's your percent increase. So 1 plus 14% would be 1.14, and then to the power of x. Okay. We're not going to make a table here because you have some messy decimals and fractions, so we're going to switch over to Desmos. But if we're starting with 350 or increasing by 14%, maybe you're going to want to go by 5 thousandths here, or we'll go by 4 thousandths for the whale population. 4,000, 8,000, 16, 20. And then let's go by, I'll go by 5 years. 5, 10, 15, 20, 25, 30. And remember, we're starting year 0 right here. That's 1981. So this data that we collected starting at year 0 will be 1981. All right, when we go to Desmos and we graph, sorry, we have 2 of them on here. I have that next example done. It's tough to see exactly where and what this graph looks like. So what I did is I clicked this gear icon, and then you can click table, and it'll give you these values, and then you could just punch in 5, 10, 15, 20, 25, 30. And I stopped at 31 because this problem said, when is a whale population going to be greater than 20,000? And hopefully you can see 30, 31, that's right when it flips from 17,832 whales to something over 20,000. So we can stop right there. I'm just going to copy these values over into Notability. I'll put them right here. Our years and whales. You can copy these down with me. Starting at year 5, 10, 15, 20, and then we'll stop right at year, 25, 30, and all the way to year 31. So we're just going to round to the nearest whole number. This was 674. Year 10 was 1298, 2,498, 4,810, 9,262. As you can see, they start to increase much more rapidly the further you go on. That's because this is an exponential representation. They're increasing more rapidly the further time moves, the further we are from 1981. Let's graph these points now. They're going to be really, really small in here. That's okay. So we're starting here at our origin, then really close to 5. 10 just barely above, 15 somewhere in the middle, 20 we're a little bit above 4,000, 25 we're now up at 9,000, so a little bit above 8, and then 30, oh I'm sorry guys, I skipped 12, 12,000, 16,000, 20,000, that's a little bit better, sorry about that. 25 is still right here at 9. Maybe we'll move it up a little bit. And then 30 all the way up at 17,000. And then 31, just a little bit past 30. We are now at our 20,000. And we're just a little bit above 20,000. So here's our exponential growth graph of the whale population in Australia, or just an Australian humpback. To answer the last part of the question, when will the population reach 20,000? You can just say after year 30, or you could say between year 30 and 31. Both of those answers are fine. But you got your function, your graph, and you analyze the graph with that last question. Okay, I want you to do the same thing for number 4. Let's start it together. Let's write the equation, and then I'll let you go graph it on Desmos. The video will pause. You can graph it on Desmos, copy the table over, and predict when the value of the truck now falls below 5,000. Okay, so the starting amount of the truck, 28,000. 1 minus our percent decrease. So 1 minus 0.095, don't forget to move your decimal 2 places to the left, would be 0.905 to the power of x. Why don't you go ahead and punch this equation into Desmos, check the graph, and then the video, hit continue, and we'll plot these same values on here together. Okay, go ahead and try this on Desmos. All right, I'm just going to go ahead and use, because we're starting at 28,000, and going down. I'm just going to have this table go by, let's do the same. We'll use 4,000. 4,000, 8,000, 12,000. Let's not skip the 16 this time. 20, 24, and 28. So now this graph's going to start up here at 28. Our first, that is the truck the brand new truck that we bought before we took it off the lot. For the table, I would maybe go by, if you looked at the graph on Desmos, you can hopefully see that it's not going to drop below 5,000 until year 17. So you have some distance to go out here. So I'm just going to go by fives again. 5, 10, 15, 20. And let's put our table here of our values. So this would be dollars for every year. Starting with 5 years, the truck was down to 16,988. Just going to round to the nearest dollar. 10 years, 10,319. 15 years, 6,265. And then 16 and 17 is where we saw the value fall below 5,000, because year 16, the truck was worth $5,669. And year 17, 5,131. Sorry, it was year 18 we saw it drop below 4,643. So let's just plot a couple of these on here. Let's do 5 at 10,000. 10,000 would be maybe right here. Year 10, oh sorry, 5 was all the way up at almost 17, my apologies. 10 was at 6,000 or 10,313. 15 at 6,000. 20, we didn't get up to 20, so we'll just go all the way up to year 18, somewhere right in the middle, and we are a little bit above 4,000, which is where the graph finally drops below the 5,000. So you could say between years 17 and 18. Okay, so plenty of problems like 3 and 4 tonight on the homework. You need to use Desmos or a graphing calculator. Check your work on the answer key, and we'll go over these together in class. Good luck.